In this video, first we will recap the last lecture, that is, subprograms part 1, and proceed to the next topics. In the last lecture, the concepts discussed are, what is meant by subprogram, how to define a subprogram, the concept of parameters, default parameters, parameter calling methods, function overloading, function overriding, etc. We started with the discussion on subprograms. A subprogram is just like function in C and C++. A subprogram or function has three concepts. First, subprogram declaration, second, subprogram definition, and third, subprogram calling. Formal parameters are dummy variables, which are listed in the subprogram declaration. An actual parameter represents a value or address used in the subprogram call statement. Next, we discussed implementing parameter calling methods. In most contemporary languages, parameter communication takes place through the runtime stack. The runtime stack is initialized and maintained by the runtime system, which is a system program that manages the execution of programs. The runtime stack is used extensively for subprogram control linkage and parameter calling. Formal parameters are characterized by one of three distinct semantic models, such as: first, in mode, in which they can receive data from corresponding actual parameters. Second, out mode, in which subprograms can transmit data to the actual parameter. And third, in out mode, in which they can do both. In the popular parameter passing methods, call by value is just like in mode, call by result is just like out mode, and call by reference is just like in out mode. Call by value parameters have their values copied into stack locations. The stack location then serves as storage for the corresponding formal parameters. Call by result parameters are implemented as the opposite of call by value. The values assigned to the call by result actual parameters are placed in the stack, where they can be retrieved by the calling program unit upon termination of the called subprogram. Call by value result parameters can be implemented directly from their semantics as a combination of call by value and call by result. The stack location for the parameters is initialized by the call, and it then used like a local variable in the called subprogram. Call by reference parameters are the simplest to implement. Only its address must be placed in the stack. And access to the formal parameters in the called subprogram is by indirect addressing from the stack location of the address. Next, we have seen the concepts of overloaded subprograms, in which the concept of function overloading was discussed. An overloaded subprogram is a subprogram that has the same name as another subprogram in the same referencing environment. Every version of an overloaded subprogram must have a unique protocol, that is, it must be different from the others in the number, order, or types of its parameters, or in its return if it is a function. The meaning of a call to an overloaded subprogram is determined by the actual parameter list. Recall, users are also allowed to write multiple versions of subprograms with the same name in other, Java, C++, and C#. Overloaded subprograms that have default parameters can lead to ambiguous subprogram calls. Let we conclude the recap of last lecture by listing the design issues of subprograms. Remember that, to have mastery over subprograms, knowledge of these design issues is must. The issues are: 1. What parameter passing methods are provided? 2. Are parameter types checked? 3. Are local variables static or dynamic? 4. What is the referencing environment of a passed subprogram? 5. Are parameter types in passed subprograms checked? 6. Can subprogram definitions be nested? 7. Can subprograms be overloaded? 8. Are subprograms allowed to be generic? 9. Is separate or independent compilation supported? Now we will start with new topics. Now, we will see the special overloading concept, which is popular in C++, that is operator overloading. An overloaded operator is one that has multiple meanings. The types of its operands determine the meaning of a particular instance of an overloaded operator. For example, if the asterisk operator has two floating point operands in a Java program, it specifies floating point multiplication. Overloading refers to multiple meanings of the same name or symbol. In a function, if name is overloaded, then it is said to be overloaded function. If symbol is overloaded, then it is said to be overloaded operator. But if the same operator has two integer operands, it specifies integer multiplication. Consider the following program in which box class was defined. In this class, an operator plus is overloaded. Observe the operator plus function in the class. Box operator plus, box ampersand b. Box tb. tb.height is equal to this height plus b.height. tb.width is equal to this width plus b.width. tb.depth is equal to this depth plus b.depth. Return tb. In the main method, two box class objects were defined, such as b1 and b2. Because of the operator plus function defined in the box class, it is possible to add both b1 and b2 objects. In general, the operator plus is used for addition of standard data type values, such as integer, float, and double. But the same plus operator is virtually used to add two objects. This is said to be operator overloading. Some standard operator overloading statements we use in C++ are cout less than operator, and cin greater than operator, used for standard output and standard input. Let us observe a class complex, that represents complex numbers, overloads plus, dot, asterisk, division to support complex arithmetic, and overloads equal, and not equal operator to support complex number comparison. Note that in C++, the operators such as dot, pointer, scope resolution operator, size of, and type ID operator cannot be overloaded. With this motivation, define the functions in the complex class given above, and complete the question 4 in tutorial 7. Next we move on to the concept, parameters that are subprogram names. In languages that allow nested subprograms, such as JavaScript, there is another issue related to subprogram names that are called as parameters. Before moving to this concept, one need to address a design issue of subprograms, that is, are parameter types checked? Let us go back to the history, in which early Pascal and Fortran 77 do not. Later versions of Pascal, Modular 2, and Fortran 90 do type checking. Other does not allow subprogram parameters. C and C++ pass pointers to functions, and parameters can be type checked. Recall that we have already discussed the use of function pointers in C programming. Java does not allow method names to be passed as parameters. The question is what referencing environment for executing the called subprogram should be used. That means, what is the correct referencing environment for a subprogram that was sent as a parameter? There are three possibilities. 1. It is that of the subprogram that enacts it, also called as shallow binding. 2. It is that of the subprogram that declared it, also called deep binding. 3. It is that of the subprogram that passed it, also called ad hoc binding, however it has been used rarely. To make the binding concept simple, make note of the following. Deep and shallow binding makes sense only when a procedure can be passed as an argument to a function. For static scoped languages, deep binding is most natural. For dynamic scoped languages, shallow binding is most natural. Deep binding binds the environment at the time a procedure is passed as an argument. Shallow binding binds the environment at the time a procedure is actually called. To understand it, consider this program. In this program, when deep binding is implemented, F3, gets the environment of f1, and prints the value of x as 10, which is local variable of f1, when shallow binding is implemented. f3 is called in f2, and hence gets the environment of f2, and prints the value of x as 6, which is local to f2. With this motivation, try to analyze the code given here. Question 1. What is the referencing environment of sub2, when it is called in sub4? Answer. This call represent shallow binding and will result output value as 4. Question 2. What is the referencing environment of sub2, when it is called in sub1? Answer. This call represent deep binding, and will result output value as 1. Question 3. What is the referencing environment of sub2, when it is called in sub3? Answer. This call represent ad hoc binding, and will result output value as 3. Generic subprograms. When a program needs to be written to sort 4 different type elements, such as integer, float, character, and double, a programmer should not need to write 4 different sort subprograms to sort 4 arrays that differ only in element type. To do this, a generic or polymorphic subprogram takes parameters of different types on different activations. Overloaded subprograms provide a particular kind of polymorphism called ad hoc polymorphism. Parametric polymorphism is provided by a subprogram that takes a generic parameter that is used in a type expression that describes the types of the parameters of the subprogram. Generic functions in C++. Generic functions in C++ have the descriptive name of template functions. C++ template functions are instantiated implicitly when the function is named in a call, or when its address is taken with the ampersand operator. Templates in C++ can be represented in 2 ways. 1. Function templates, and 2. Class templates. The syntax for declaring a template function is similar to that for a template class. Template type func_name, type arg1. For instance, to declare a template function to add 2 values together, you could use the following syntax. Template type add, type A, type B. Return A plus B. Now, when you actually use the add function, you can simply treat it like any other function because the desired type is also the type given for the arguments. This means that upon compiling the code, the compiler will know what type is desired. Int x is equal to add 1, 2. Will correctly deduce that type should be int. This would be the equivalent of saying int x is equal to add 1, 2. For example, if you want to make the first function calling as default, you need to declare the default type as integer, as follows. Template type add, type A, type B. Return A plus B. Let us now consider the generic class. Consider the following code. The class represents a generic stack, in which the elements are inserted and removed in last in first out fashion. Questions are: 1. What is the default stack type it is? Answer: since the default type in the template class is integer, it is an integer stack by default. 2. How this stack can be used for float values? Answer: instantiate the stack template class using float. That is stack f stack. 3. Now, your task is to define this template class. The following is the C++ version of the generic sort subprogram. This generic subprogram takes any type of unsorted array, and returns sorted array. Coroutines. A coroutine is a subprogram that has multiple entries, and controls them itself. It is also called symmetric control. It also has the means to maintain their status between activation. This means that coroutines must be history sensitive, and thus have static local variables. Secondary executions of a coroutine often begin at points other than its beginning. A coroutine call is named as resume. The first resume of a coroutine is to its beginning, but subsequent calls enter at the point just after the last executed statement in the coroutine. Some other properties of coroutines are: typically, coroutines repeatedly resume each other, possibly forever. Coroutines provide quasi-concurrent execution of program units, the coroutines. Coroutines execution is interleaved, but not overlapped. Now let us see an example. In this figure, you can observe that the resume from master started with coroutine A. In this, resume B is called, hence, the control is shifted to coroutine B. However, in B, coroutine A is resumed, thereby the control is shifted to coroutine A. Likewise, in this figure the resume from master is started with coroutine B, and according to the resuming coroutines, multiple entries and exists takes place. Let us now discuss some other related concepts of subprograms. First we will see multidimensional arrays as parameters. If a multidimensional array is passed to a subprogram, and the subprogram is separately compiled, the compiler needs to know the declared size of that array, to build the storage mapping function. In the programming languages like C and C++, programmer is required to include the declared sizes of all but the first subscript in the actual parameter. The main drawback of this method is that it disallows writing flexible subprograms. Hence, a solution to overcome this problem is pass a pointer to the array and the sizes of the dimensions as other parameters. The user must include the storage mapping function, which is in terms of the size parameters. Next, we will see design considerations for parameter passing. There are two things to consider, such as 1. Efficiency. 2. One-way or two-way parameter passing. However, these two are in conflict with one another. But a good programming represents limited access to variables, which means one way whenever possible. On the other hand, efficiency represents use of pass by reference, which is fastest way to pass structures of significant size. Next, we will see the concept of binding and possible binding times. The concept of binding. A binding is an association, such as between an attribute and an entity, or between an operation and a symbol. An entity could be a variable or a function or even a class. Binding time, it is the time at which a binding takes place. Possible binding times are: language design time, example, bind operator symbols to operations. Language implementation time, example, bind floating point type to a representation. Compile time, example, bind a variable to a type in C or Java. Load time, example, bind a Fortran 77 variable to a memory cell, or a C static variable. Runtime, example, bind a non-static local variable to a memory cell. Static and dynamic binding. A binding is static if it first occurs before runtime and remains unchanged throughout program execution. A binding is dynamic if it first occurs during execution or can change during execution of the program. Next, we will see type checking. Type checking. It generalized the concept of operands and operators to include subprograms and assignments. Type checking is the activity of ensuring that the operands of an operator are of compatible types. A compatible type is one that is either legal for the operator, or is allowed under language rules to be implicitly converted, by compiler-generated code, to a legal type. A type error is the application of an operator to an operand of an inappropriate type. When is type checking done? If all type bindings are static, nearly all type checking can be static, done at compile time. If type bindings are dynamic, type checking must be dynamic, done at runtime. A programming language is strongly typed if type errors are always detected. Advantage of type checking is, allows the detection of misuse of variables that result in type errors. Coercion. The automatic conversion between types is called coercion. Coercion rules will weaken typing considerably. Why coming to the programming, C and C++ allow both widening and narrowing coercions. Where Java allows only widening coercions, and Java's straw-in typing is still far less effective than that of other dynamic type binding. It provides a lot of flexibility. Programming languages like Perl, JavaScript and PHP, Scheme uses dynamic type binding. Next, we will see the concept of storage bindings and lifetime. The lifetime of a variable is the time during which it is bound to a particular memory cell. Allocation, getting a cell from some pool of available cells. Deallocation, putting a cell back into the pool. Depending on the language, allocation can be either controlled by the programmer or done automatically. Categories of variables by lifetimes are as follows. 1. Static lifetime is same as that of the program. 2. Stack dynamic lifetime is duration of subprogram. 3. Explicit heap dynamic allocated and deallocated by explicit directives, specified by the programmer, which take effect during execution. 4. Implicit heap dynamic allocation and deallocation caused by assignment statements. Variable scope. The scope of a variable is the range of statements over which it is visible. The non-local variables of a program unit are those that are visible but not declared there. The scope rules of a language determine how references to names are associated with variables. Note that scope and lifetime are sometimes closely related, but are different concepts. Static scope. The scope of a variable can be determined from the program text. To connect a name reference to a variable, you, or the compiler, must find the declaration. Search process, search declarations, first locally, then in increasingly larger enclosing scopes, until one is found for the given name. Enclosing static scopes, to a specific scope, are called its static ancestors. The nearest static ancestor is called a static parent. Scope and shadowed variables. Variables can be hidden from a unit by having a closer variable with the same name. C++, Java and other allow access to some of these hidden variables, such as follows. In other, unit.name. In C++, class underscore name scope resolution operator name, or scope resolution operator name for globals. In Java, this .name for variables declared at class level. Next, we will see static scoping and nested functions. Consider the following nested function. Assume that main calls A and B. A calls C and D. B calls A and E. Now we will see nested functions and maintainability. Assume that, suppose the specification is changed, so that D must now access some data in B. If so, how it is maintained? Solutions are: 1. Put D in B, but then C can no longer call it and D cannot access A's variables. 2. Move the data from B that D needs to main, but then all procedures can access them. But it is for procedure access. However, using nested functions with static scoping often encourages many global variables. But it is not considered to be good programming practice. To address this, current thinking is that we can accomplish the same thing better with modules, or classes. In this context, static scoping is still preferred to the alternative. Most current languages use static scoping at the block level, even if they don't allow nested functions. Conclusion of the subprograms chapter. Here is the summary of what has been covered in this lecture. A subprogram is a component of a program that carries out a specific activity, or set of related activities. With the exception of coroutines and concurrent calls, a typical subprogram exhibits the following properties. Single entry point, invoked by a call statement, upon completion. Control is returned to the calling statement, may be defined with parameters that would require matching arguments on the call statement. May after execution, return a set of values to the calling statement. For language, there are housekeeping procedures that have to be followed when subprograms are called. Commonly known subprogram structures are separate subprograms, integrated nested subprograms, integrated independent subprograms, and non-separated subprograms. Parameter handling strategies that have been identified include the following: pass by value, pass by result, pass by reference, pass by name, and pass by value result. A language may exhibit multiple strategies. Since this is an important design issue, it must be decided early in the design stage of a language. When learning the language, it is important for the computer science professional to recognize what strategies are being employed by the language. All contemporary programming languages support the principle of recursion. In learning a new language, it is important to observe how recursion is supported in the language. Some languages support programmer initiator overloading, operator overloading programs. Some languages support coroutines. This feature can be useful in parallel processing.